Okay, so in this video, we would like to compute the Q-binomial coefficients. So let's recall the definition that we have. So we said that M plus K choose M is the Q polynomial that corresponds to all partitions containing the M by K grid. And L here is the length of the partition. And here, when we talk about partition, we really mean the Young diagrams that are contained in the M by K grid. So we have seen an important property of these coefficients. So we have seen that M plus K choose M is the same thing as M plus M minus 1 plus K over M minus 1. This corresponds to the paths that have the first vertical step. So we recall that partitions correspond also to paths starting from the lower left corner and proceeding toward the upper right corner. And if our first step is vertical, then this is how many these are the Q polynomials that correspond to the vertical step, the vertical first step. And then we have the case of a horizontal first step, where we have M plus K minus 1 choose M times Q to the M. Okay, so this is pretty much the formula that we're going to use in an inductive way in order to compute these partitions. First of all, to make our computation a little simpler, let's define the Q integer numbers. So the Q integer number n, so for n in n, is by definition the n choose 1. In order to understand this in our context, we need to write it as 1 plus n minus 1 choose 1, which means that we have the partitions that are contained in the 1 by n minus 1 grid. And again, we computed this earlier. So this will pretty much give us 1 plus q plus all the way to q to the n minus 1, which is 1 minus q to the n over 1 minus q. So these integer numbers n are going to be pretty much 1 minus q to the n over 1 minus q. And we also define 0 to be simply 1. Okay, it's very important to understand here that m plus n in general is different from m plus n. So this definition actually is not additive. And for that, we would have to use the formula that we gave before. So basically, for these numbers, we will have m plus n can be given in two ways. Either it can be m plus q to the m times n, or it can be n plus q to the n times m. And of course, this can be proven by a simple computation. So this is part of this combinatorial identity, but it wouldn't be hard to actually prove it directly. So let's just do it so that we can see how it's done. So here we have 1 minus q to the m plus n over 1 minus q. And the trick here is that we can add and subtract either q to the m or q to the n. So this will be 1 minus q to the n plus q to the n minus q to the m plus n over 1 minus q. And this is 1 minus q to the n over 1 minus q. And now we factor out q to the n from here, and we get 1 minus q to the m over 1 minus q. And of course, this is the same thing as n plus q to the n times m. And of course, had we added and subtracted q to the m, we would have gotten the other identity. Again, this is contained in this combinatorial identity, but since the algebraic expression is so simple, we might as well do it this way too. The next thing that we would like to define is actually, even this definition here, I'm not sure that it's needed in any particular setup. So or we might actually put it back. So in any case, let's also define the factorial of these q numbers to simply be 1 factorial times 1 times 2 times all the way to n. And this is where we might want to give the definition of 0 factorial being equal to 1. So that's the only time that we might want to define this. So basically, our goal is to show that we have a very an identity which is very similar to our usual identity, meaning we would like to show that this is m plus n factorial over m factorial times n factorial. And pretty much the idea here is that this can be proven in a completely algebraic way by using induction and this formula right here. Okay, so so how do we do this? So let's prove this. So start with m plus n, choose m, and use our identity. So this is going to be the same as m minus 1 plus n choose m minus 1 plus m plus n minus 1 choose m times q to the m. Okay, so now we proceed with our inductive hypothesis. So we think that this has been proven for all pairs of numbers that adapt to something less than m plus n. And this would imply that this is the same thing as m plus n minus 1 factorial, this q factorial that we're talking about, over m minus 1 factorial times n factorial plus m plus n minus 1 factorial over m factorial times n minus 1 factorial times q to the m. So now we can factor out what n m, oops, sorry about this, and m plus n minus 1 factorial over m minus 1 factorial times n minus 1 factorial. And inside, we will have 1 over n plus 1 over m times q to the m, right? And here we can clear denominators. And we will have m plus n minus 1 over m minus 1 factorial times n minus 1 factorial, and times m plus n q to the m over n times m. And we're pretty much done, because by the identity that we gave a moment ago, this will be, the top will be exactly this, and the bottom will be this product times this other product. And of course, this is exactly the same thing as this. Okay, so now we proved the identity that we wanted, and our contention is that this identity now can very easily give us a very nice expression for this, because for the Q binomial coefficient, because now we will have so this will give us 1 minus q over 1 minus q times 1 minus q squared over 1 minus q, all the way to 1 minus q to the m plus n over 1 minus q, and on the denominator we have 1 minus q over 1 minus q times all the way to 1 minus q to the m over 1 minus q to the q times 1 minus q times 1 minus q to the n over 1 minus q. And now we can have any of the two possible cancellations. So first of all the 1 minus q's cancel with the 1 minus q's that we have here. And we can pretty much cancel the m's, or cancel the m first factors or the n last factors. It's really up to us. But the bottom line is that we will have 1 minus q to the m plus n, going all the way to 1 minus q to the m plus 1 over 1 minus q times 1 minus q to the n. And that's our formula. Thanks for watching.